is Abdullah Sanawi.
Pedro Legeri. This is George Mill.
Our final senior design is a three-dimensional double parabola solar collector, in which we use thermal radiation that we obtain from the sun to reduce steam for energy. In this three-dimensional solar collector, range of focal point is created by reflecting solar radiation into a certain angle. A number of copper tubes, 5 feet each, 5 feet long each is 5 feet long, running through a straight line path of focal points so that steam can be produced at the outlet of the system. One purpose of our solar collector is of building this design is to minimize the cost of solar collector. Today, most of the solar collectors that are used in industries require a controlling system or some tracker to collect solar energy for the longest period of the day as the sun's position is shifted. However, in our solar collector design, controlling system is not needed due to the three-dimensional shape we built our design with. In order to achieve best results of this design, taking the maximum benefits of solar energy is required. Therefore, taking the maximum benefits of heat transfer factor is required for this design. Therefore, combined effects of conduction, convection, and radiation will be used in this design, and this will be explained in detail by my colleague Pedro Legeri. And last but not least, we use concentrated sunlight located at the focal point for maximum radiation observation. Our motivation for this design is that today's statistics show that availability of fossil fuel is decreasing, leading to high demands for renewable energy, and also we're looking into reducing dependency on imported energy such as crude oil, and also reduce the environmental impact of fossil fuel consumption and harvesting. We set our objectives for this design as following: design an efficient and low-cost solar collector, design and manufacture a compact solar collector, and minimize cost efficiency to harvest thermal energy, and to significantly raise the temperature of water so that we can produce steam for clean energy. Our global learning for this design is that the capability of installing our design in most regions of the world where vast areas are rich in sunshine, so that we can use solar energy to address multiple problems such as climate change, environmental pollution, and world economy.
All right, so there's some previous designs of the solar collector. We have the Parabola trough solar collector, evacuate tube solar collector, flat plate solar collector, and solar tower. The amount of energy that hits the solar energy that hits the Earth's surface is about 1,000 watts per meter squared, depending on weather conditions and locations. So really good heat absorber is needed. So for the first alternative design, we used the hyperbolic shaped solar collector, and it's going to be made entirely with copper. They're going to be helical copper tube circulating inside the copper, the hyperbolic shape, and connected to that is another copper tube circling around the focal point of the parabola. After several tests, we concluded that this design didn't give us the desired results based on many reasons. For one, the focal point is effective only at a certain point of time when the sun's rays enter the mirror parallel to its plane of symmetry. So therefore it defeated the purpose of our main goal, which is effectively using the focal point. For our proposed design, we wanted to upgrade and modify the current version of the parabolic trough solar collector. So what we did after several tests and designs and experimenting, we came to the conclusion that if you connect two parabolas next to each other and rotate them at an angle of 55 degrees from their plane of symmetry, we're going to have a common focal point line right here at the bottom. Therefore, the sun will always hit the straight path, line path of the focal point whenever it reflects from the parabolic mirror. We chose the dimensions to be about like 3 by 4 feet because we want the focal point line path to be 6 inches. So we want to prove that our design works. So what we did is we did some tests using a laser, a printed design, and a mirror sheet. And our result proved that whenever you rotate the laser, it always hit the straight line path of the focal point. As you can see here, the laser is here, it reflects back here onto the focal point in the yellow line. So, as I mentioned before, copper is a really good heat absorber, so we decided to install the copper tubes horizontally along the focal point line path, and it's going to be heated by convection and conduction. Also, the concentrated sunlight is also going to be reflected, and it's going to heat the tubes by radiation. We're also going to be using a cover on top of our system made of acrylic sheets for the purpose of retaining the solar radiation inside the system and increase the efficiency.
All right, so as Matt or my colleague explained, our driving dimension for our construction was the focal point. So on the basis of a 6-inch focal point, we were able to select the dimensions of our parabola and accordingly select our materials. So the very first step was to print out a large real-size printout of our parabola, which we then used as a guide. We taped on top of plywood. We bought 5-pine plywood for the frame of our collector. The very first step was cutting out the inside of the parabola and using it as a guide, as you can see here, to cut with a jigsaw through the plywood and make 3 frames. Next, please. So here you can see the 3 frames. The next step was the attachment of the surface. For the surface, we used a 6-foot by 3-foot 26-gauge zinc metal, which we attached directly onto the frames using roofing nails due to their flat heads, which was beneficial for our design to keep the actual reflecting surface as flat as possible. After finishing our collector surface, the next step was the construction of our piping system. Here we can see we used 5-foot copper pipes with 1/2-inch diameter, and we joined it at the ends with 90-degree bends, along with a small piece of pipe to put them together. And all of this was sealed using silver solder. Here we came into the first step of our design, which was the piping system. As you can see, the pipe is supported at the inlet and outlet by the sides of the collector. And at the beginning, these supports weren't there, and the weight of the pipes made them buckle under their own weight. So we thought of using small sections of pipe in between them to give them more rigidity. This allowed for our structure to be strong. The very next step was the attachment of the actual reflective surface. We used contact cement due to its properties because it allowed us to apply the glue and gave us a 15-minute time window to attach the reflective surface. We cut 4 pieces of mylar, our reflective film, each one the size of each metal sheet, which we then attached individually to form the surface of the collector. The very last step, next please, the very last step was the construction of the base, which we used a 4x4 plywood piece, which we cut in half. Then we drilled the base along with the collector frame, which you can see here, to install a large bolt to use as a pivot to be able to rotate our structure. Next, please. Here we can see the final stages of the prototype construction. Here you see the collector surface without the sides, and here you see with the sides and the pipes installed. And here you can see the installment of the glass cover on top, which was almost the size of the top entry, but we used some metal plates which we attached to the ends for it to rest on top.
For the prototype testing, we did 2 tests at 2 different times. First test was the comparison between a black painted copper tube and a pure copper tube. Our theoretical results showed us that the end result should be 112 degrees Celsius, and our experimental results gave us a 98 degrees Celsius. This figure shows the experimental results at a constant flow rate at the 12 p.m. Clearly shows that black painted copper tube is, as shown in the blue lines, gave us a higher temperature than the pure copper. At the second test, we did not rotate our prototype. We kept it at a fixed angle. At 3 p.m., the sun changed direction. It came a little bit lower. So for the theoretical results, we're supposed to get 96.4, but our experimental results gave us an 86 degrees Celsius. Because some of the rays were reflected on the copper tubes because of the angle of the sun. So, and we still got a really high results because of that. In this figure, it shows the experimental results at constant flow rate at 3 p.m. And clearly shows again that the black painted copper tube is still better than the pure copper tube. This is a simulation of the copper tubes when it's the maximum absorption. A maximum temperature of 117 degrees Celsius was obtained through SolidWorks simulation. This is a video of our testing. As you can, as soon as we opened the valve, you could clearly see really high temperature of water, including some of steam. And the highest temperature we got here was 98 degrees Celsius. So some of the improvements of our design, we can always seal the leaks. Whereas one point of our copper tubes, there was some leak of water that gave us a little bit of reduction of the pressure and temperature. We can always seal that, and we also can seal the system because maybe some wind have entered our system, therefore we get a little bit lower temperature than expected. Another improvement is we can also install copper plates on the sides of the copper tubes, and this will help the conduction and close all the gaps of space that was lost because of the sun rays, because of the spacing. Also, we can also install copper tube surrounding with selective coating. This tube features a vacuum, and it reduces the copper oxidation and also prevent the heat loss from the pipes. And also, some of our results on experimenting calculations, if we doubled our design is like 6 feet long. If we doubled it, we're probably going to have a temperature of maybe 140 degrees Celsius based on our calculations.
All right, so as you all know, in order for the proper functioning of any design during the design process, the standards must be followed. We followed the ISO, International Standardization Organization standard for solar energy for solar thermal collectors, as well as a local organization who also deals with standards for solar collectors, which is the FSCC. Here are just a few of the test sections that are in the ISO solar collector standards that we followed, as well as the FSCC. Right. So, following, we have a cost analysis of our project. It's duly noted that only the main components are here, which are the sheeting, the film, the tubing, the bends, and the plywood and the valves. However, more additional costs can be added to that in our project due to tools and other miscellaneous parts such as nuts, bolts, and screws, which obviously in the mass production of our system will not be included. And also we have accountability of the number of hours that was spent by each of the teams if we wanted to charge you 4 hours. So in conclusion, we can see that our project is a continuous design effort, not only in the scope of our project, but also the entire field. During our design progress, we encountered several setbacks which made us improve our design. And also in the field, this is applicable because the designing of appropriate and affordable technologies for areas that are poor of resources always has to be an important focus for any organizations that tackle these challenges. The vast areas of the world are rich in sunlight, and they could benefit greatly from simple, affordable, and durable solar appliances. We were able to yield significant results despite the imperfection of our design, because of our limited manufacturing capabilities, our design could have been produced much more skillfully, but despite that, we still got great results. The development of technologies like this is important to move the world trend towards free energy, and the application of our design, we believe, can be applied anywhere in the world as long as there's sunlight. So our objectives for the future, as you know, we weren't able to produce a continuous flow of steam. So one objective would be to improve the efficiency of our design for that purpose. And furthermore, the closing of the ranking cycle in order to produce a zero emissions energy system, which would be to add a condenser and a pump to be able to create a closed cycle between the collector and its other pipes. Any questions?
You said you suffered a lot of setbacks. Okay, what did you learn most from those setbacks?
Well, what I learned most, I guess, proper schedule, planification, learning to deal with different, the skills and the strengths of different team members. Also, well, the main setback was the piping system, that we had to change that. We were able to come up with a solution. And apart from that, well, we had some leaks in the system that we tried to fix many times, but we didn't have the best soldering abilities, and that was one of the main things that we couldn't fix.
I didn't see any numbers in regards to mass flow rate or water volume going through there.
I didn't mention that, but it's listed in one of the tables.
So you actually found an optimal
Yeah, exactly.
flow rate?
Exactly. We found an optimal flow
Because
rate.
what I've seen done
Lower-
before is you actually, instead of heating the actual water directly, you heat oil, and you loop the oil back and forth until it heats up enough to heat water on an exchanger, and then that creates the steam, as opposed to trying to create the steam directly through the sun. You understand what I'm saying?
Yeah.
So if you heat the oil to 400 degrees, for example, right, because it's in a closed loop and it's getting reheated constantly all the time, then you got a heat exchanger heating your water, and you'll get steam a lot easier than trying to pump the water through there, and then you have losses through the vapor, and you can't pump vapor, you know. But it's a good analysis. But
Yeah, we were
Did you look
trying to
into that
keep
at all,
the cost
other
as
options?
low as possible, trying to keep it the least amount of components possible to see if we could make a very cheap design.
Cost
that
efficiency.
could
But
be
it has to
easily
work.
applied.
Yeah.
Of course.
That's
and
where
then,
it is, but-
you know, you were showing that your experimental results didn't get to steam, it's 98 degrees. And then you're saying we were expecting 140 if you doubled it, but that doesn't really match what you got as a result as well either, because you're looking at numerical analysis. So, I don't know, I mean, it's a good exercise, but you gotta think, you know.
All right, so first things first, thank you guys. You know my main complaint before, right? So your alternate design changed to the double parabola, and if I remember correctly, I may be completely off, the alternate design that you guys proposed before was presented last semester in a different capacity, and they got 140F, right? And you guys are now up to almost 200, right? From what I remember, I may be completely wrong. But anyway, thanks. People may not know, but I was a little critical of that.
Yeah, we took that into
I
consideration.
appreciate you thinking of it. I don't know if you changed it because of that comment, but I think you did. Right? Sorry. So I just have one question. How? You probably don't have this answer. I'm just curious. So you came up with a solution to try to create steam, right? I think there's other solutions for using the sun's energy, for instance, photovoltaics and things like that, right? Is there any correlation or comparison that you guys can do between your system and that system? So for instance, if I were to have a photovoltaic system, right, could I heat water and create steam using the output voltage from that system pretty easily? And how does it compare to what you guys are doing, I guess is the main question, right? In terms of cost, right, main cost.
Well, like, our design is like a lot cheaper than a PV, right? Also like for maintenance, and for PV like photovoltaic, like I believe like every like period of time you have to maintain or change. But in this design, like as you can see, is like simple components that you don't have to worry about the cost. Like cost efficiency is like one of the most goal in this design.
Right, but you also have to meet some specific set of standards, right? So do you feel like the output steam that you're getting could match the efficiency of those systems?
Well, the
It's
Maybe-
tough, it's a tough
It's
fix.
a tough, yeah, but it's because our main objective is costs.
Right.
Like I said, we definitely could use a tracker, but we'll definitely keep the results as optimum. But like I said before, our main goal is the cost. So people who can afford the trackers can only use our design and maybe get some better results.
Okay, thanks.
You mentioned that the black painted copper performed better than the normal copper. Was that what you expected?
Yes.
Okay. And why?
Painted in black it gives us more thermal conductivity based on a lot of research, and we did a lot of research, and some previous parabolic solar collector always used black.
like high emissivity from radiation.
So basically, we thought that the copper tubes conducted heat very quickly, so as fast as they could absorb heat, they could also dissipate it. So we thought that this black paint would be helpful. It was high heat paint that's used for engine components and things that withstand high heat. And gratefully, after results, they determined that that was helpful for the retention of heat in the pipes.